Okay, so the idea now is to talk about the extended Euclidean algorithm. After we talked about the Euclidean algorithm, now we're going to talk about the extended Euclidean algorithm, which after we did Euclidean algorithm, will let us find two integers, x and y, such that the greatest common divisor of two integers a and b will be equal what the Euclidean algorithm gives us, and we have a video about it. And now we are going to get what combination, what two numbers we can multiply the numbers that we did the greatest common divisor on, such that their combination will give us the value of the greatest common divisor. You can see this a is here, this b is here. What combinations, in what integer to multiply each one of them and then combine them to get the value of the greatest common divisor. It can be found, this idea, for example, in RSA algorithm, in cryptography, so it is useful for some things. So this is the motivation for why we want to get the linear combination of those two numbers to get the value of the result of the greatest common divisor, the GCD of those two numbers. Those coefficients that we find using the extended Euclidean algorithm, x and y, those two integers, are called the Bezold coefficients, another name for them. So we want to find those x and y, those two coefficients. Using them, this sum will give us the GCD of a and b. Okay, this is the idea of the extended Euclidean algorithm. So what we're going to do, we need to firstly find the GCD of a and b. So we will apply the Euclidean algorithm for GCD of a and b, greatest common divisor of those two numbers. And after doing this, we will use the result, and we will see now how backwards to get those two coefficients such that the sum of the multiplication of those two will give the greatest common divisor of the two numbers a and b. Okay, so let's start with an example, or we'll use the example to show how we are doing this backwards. So let's get the greatest common divisor of 252, this will be our a, and 105, this will be our b, and we want to find x and y, those coefficients, such that the linear combination of those two numbers will give me the greatest common divisor of these two numbers, which is, I tell you, 21. So we start by applying the Euclidean algorithm for finding the greatest common divisor. Here it is, let's do it. For 252 and 105, in this case a is 252 and b is 105. So we are doing the Euclidean algorithm. Take a, take b, divide 252 by 105. It's 2 with a remainder of 42. Because the remainder is not 0, we need to continue, and we didn't finish. What we're doing, taking this value, put it right over here. Taking this value, replace it with the b, so right over here, and calculating 105 divided by 42. The quotation is 2, and the remainder is 21. Again, because the remainder is not 0, we are not finished of the Euclidean algorithm. We didn't yet get the result for the greatest common divisor. So what we're going to do is take the 42, this is the b part, and replace it with the a part. Taking the r part, replace it with the b part, and 42 divided by 21 is 2 with a remainder of 0. Because the remainder is 0, we are finished, and the result is what is in b, which is 21. So the greatest common divisor of those two numbers is this 21. This is the Euclidean algorithm. This is the part that we applied the Euclidean algorithm. This is the step 1 that we saw. Now we are going to use the result of what we did and going backward to find those two coefficients. Let's do it. So we start by saying that look at this equation. We can isolate this 21. Okay, this equation isolating 21 give me 105, which is the b, yes, 105 is the b. So isolating the b, this is the b, and isolating the greatest common divisor, the result will give me 21 equals 105, which is b, minus 42 times 2. Now, this 42 is not a and b. I want here the greatest common divisor, and here I want to see only a and b multiplied by something. Those are the coefficients. So I need to get rid of this 42 and get instead a and b. So I need to define this 42 by a and b. This equation, this is a, this is b. So this equation will let me replace this 42 that I want to get rid of here by using a and b, and this is what I want. So let's take 42, isolate it, and replace the value here with what I get right over here. So let's do it. 42 equals 252, and take this to the left side, getting this. So now I can replace this value by those two, and don't forget to multiply by 2, because this is what we got from the equation. So we are doing it and multiplying by 2. So 21 equals 105 minus 2, which is right over here, multiplied by what we replace 42 with, right over here. Now opening up, getting, this is 105, and this is 4 105, and this is 2 times 252 with the minus. So this is what we get. And now let's organize this a bit. This in the side, in this side there is the 21, which is the GCD of the A and B, and in the other side, on the other side, we have 5 times B minus 2 times our A. If we organize it, so 21, which is this GCD of our A and B, equals a coefficient, which is the x, because this is the coefficient of A, minus 2 times A, 252, plus a coefficient of B, so it's y, times our B value 105. And here you can see that I got what I wanted. I wanted to define, to represent our GCD by the A and B on which the GCD worked on, with coefficients, which are x and y. And this is exactly what I got. So here I define my GCD as a linear sum of a linear combination of A and B. So this is what the extended Euclidean algorithm did. We want to find coefficients such that the GCD of A and B equals AX plus BY. So we did the GCD, we got this value, and we use all the process here to go backwards to get the result of the coefficient as we wanted. In this example, we isolated the GCD and we replaced all the things in the equations by coefficients and A and B, and this is how we represented the GCD using our A and B and got this. Now it is used, for example, in RSA, in cryptography, this idea of representing my GCD of two numbers by linear combination of the two with coefficients. And this is it. Thank you very much. This was about the extended Euclidean algorithm, which uses the Euclidean algorithm. Thank you very much, and this is it.